So we are going to talk about the central limit theorem now. What does central limit theorem say? Actually, I mean, Ata, maybe you have heard about the central limit theorem in today's course, in the earlier courses of simulation, and also at the times that you have taken the statistics course. So it says, let x1, x2, x3, so on and so forth be a sequence of independent and identically distributed random variables, just like before, just like the weak law of large numbers. So we have a sequence of random variables. They are independent from each other, but they are identically distributed. They are distributed with the same distribution. Each of these random variables have a finite mean, which is mu. Each of these random variables has the expected value of mu and variance of sigma square. Now, we are writing here something very interesting. So what is this thing? We are writing here x1 plus x2 plus blah blah xn, which is the sum of these n random variables. So we have the first n of these random variables is summed up. Remember now, each of these random variables has the expected value of mu, and after summing these random variables up, we are dividing this summation, we are subtracting n times mu from this summation. So we are basically subtracting the expected value times n. Basically, for each random variable that is in the sum, we are subtracting the expected value at that quantity, okay? Then we divide that difference to the sigma square root of n, okay? Sigma square root of n. And central limit theorem tells me that this value here, this value that we calculate here, this random value obtained by the first n random variables in the sequence, is going to behave as a standard normal random variable as n goes large and large. So if this n is large enough, if the number of random variables that we put in the summation is large enough, then this value is going to be a standard normal random variable. Actually, it is going to be a random variable because it is a function of random variables, but it is also going to be a normal random variable, the question states, okay? Standard normal random variable, in fact. Or in other words, if we intend to calculate the probability of that formulation given here, to be less than or equal to x, that probability will be calculated by the integral of the standard normal probability density function from minus infinity to x, or you can directly use the cumulative distribution function from the table at x. But this is only going to be possible when n is sufficiently large, it says. Okay? In other words, my friends. So let me explain this situation to you. Now you see, we have the summation of these random variables, right? x1 plus x2 plus x3, so on and so forth. Now, I'm just going to open a paint file, and from there, I just want to show you that. What is the... So let me expand this page a little. What is the expected value of x1 plus x2 plus blah, 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 xn? So what is the expected value of the sum of these n random variables in the beginning of the sequence? It is just going to be equal to a summation I from 1 to n of individual expectations, right? The summation of individual expectations. And each individual expectation here is mu. And that is going to be, n times mu. Okay? And how about the variance? How about the variance of x1 plus x2 plus xn? Now it is going to be the sum of the variances, right? The sum of the variances, I from 1 to n, the sum of the variances for each of these random variables plus we have what? Covariance term. So we have the covariance term here. But I'm not writing it because, I mean, I'm getting tired when writing these complicated statements in this paid file. Because I'm not writing here. This covariance term is simply going to be equal to 0 because these random variables are independent from each other according to the text. So therefore, it is just going to be equal to the sum of the variances. And each variance here is sigma square. Each of these random variables have the variance of sigma square. And the sum of n sigma square values is going to be n sigma squares, right? Now, the expected value of the sum is n times mu. The variance of the sum is n times sigma square. And in fact, you can write that the standard deviation of the sum, is the square root of the variance, which is going to be sigma times square root of n, right? So we have these values obtained here. And in fact, when you look at this picture, when you look at this formulation, we are basically subtracting the expected value of the summation of these n random variables, and we are dividing this difference to the standard deviation of the sum of these random variables, which totally looks like the standardization operation that we are doing for the normal random variables, right? So this is a standardization procedure here. This complicated formula is not too complicated, actually. What we are doing here is we are subtracting the expected value of the sum of these random variables from the sum and dividing the difference to the standard deviation of the sum of these random variables, which is sigma times square root of n, which is basically a standardization. And after this standardization operation, that is going to be related to a standard normal, the probability statement is going to be related to a standard normal random variable. But this is going to happen when n goes to infinity, it says. So not just for the summation of 3, 4, 5, or 6 random variables. That summation requires a sufficiently large number of random variables. Okay? Now, as I have shown you on the paint, the central limit theorem states that x1 plus x2 plus x3 until xn is going to behave as a normal distribution with location parameter n mu and scale parameter sigma times square root of n, because this is the expected value of the sum and this is the variance of the sum. And the central limit theorem states that if we have a sufficiently large number of independent and identically distributed random variables, the summation is going to be normally distributed. In short, the shortest possible explanation of the central limit theorem: the sum of a sufficiently large number of independent and identically distributed random variables is normally distributed. Okay? Now, you know, average of observations, average of a bunch of quantities is simply what? How do you calculate the average of these values? You sum them up, then you divide it to n, right? I mean, when you multiply the summation of components with 1 over n, you get the average. Now, remember, when you multiply a normal random variable with a constant, that normal random variable, the new normal random variable, the new variable is still going to be normal. So therefore, if the sum of a sufficiently large number of IID random variables is normally distributed, then the average should also be normally distributed. Okay? So basically, I am mentioning about here, if according to the text, the summation of a sufficiently large number of independent and identically distributed random variables, so as n goes to infinity, I say, and these are IID, these random variables are IID, is going to be normally distributed with location parameter that is equal to n mu, and the scale parameter is going to be sigma times square root of n. Okay? And how about the average? which is the summation of xi values and divided by n. Now, basically, we are multiplying the summation with 1 over n. Now, as n goes to infinity again, as n goes to infinity, and these random variables are assumed to be IIT, in that case, this also going to be a normally distributed random variable, and its expected value will be 1 over n times the expected value of n mu, which is going to be mu, and its standard deviation is going to be 1 over n square. So remember, what is the variance of x bar? So you can take 1 over n outside the variance. It is going to be 1 over n squared, the variance of that value. And standard deviation is going to be 1 over n times sigma square root of n. That is going to be sigma over square root of n. Okay. So both the summation and the average of independent and identically distributed random variables is normally distributed, but with different parameters here. Okay, now the history of the central limit theorem and the proof of it can be found in the textbook. I think 2 or 3 pages are left for that proof. It is not an easy proof. The central limit theorem's proof is not an easy proof, but I recommend you to read it because this is one of the important theorems about data science and statistics for you to understand.